In this video, we're going to talk about algorithms. So let's start by defining an algorithm, and that's what chapter 3 is kind of devoted to studying is algorithms. An algorithm is a finite set of precise instructions for performing a computation or solving a problem. Well, as a computer science major, that probably seems very important to you. A precise set of instructions kind of is what code becomes. All right, so let's look at an example. Let's describe an algorithm for finding the maximum value in a finite sequence of integers. So we're looking at a sequence of numbers, and we're going to assume that they're not in order. So to figure out which one's the maximum, we would set the temporary maximum to be the very first integer in the sequence, then compare it to the next integer. And if the next integer is higher, we set that one to be the maximum. And then we're going to repeat that until we're done with the integers. And once we're done, whatever we have as our temporary max, that's going to be called the largest integer in the sequence. So that is what is going to be the answer. Okay. Real quick, before we move on, I don't know if I've ever mentioned, but I was a history major when I first started off in school. So I love historical references, and our book actually has a lot. If you ever want to read up on any of the mathematicians and scientists and computer scientists who have contributed to the field, it's fascinating read. But this particular mathematician, and I'm going to call him by his last name, Al-Khwarizmi, he has a strong association with algebra. He actually wrote a book that kind of defined what the modern day algebra is. And in the title of the book, we stole the word algebra. Okay. But his name, Al-Khwarizmi, they kind of, I hate to say it, but bastardized the name. And that's where they got algorithm, the word algorithm. So he not only gave us algebra, but he also gave us the word, our modern word that we use, algorithm. Okay, there we go. So note, algorithms can be specified in different ways. Their steps can be described in English or pseudocode. So this book, in an attempt to kind of prepare for the connection between what we're doing and computer science, devotes itself to using this kind of pseudocode. Now, this pseudocode can actually be found in Appendix 3. There's quite a nice bit of information there. In fact, I pulled this right here from Appendix 3. And oh, sorry, I thought I wrote a 3, but I guess I didn't. Appendix 3. It just gives a list of kind of pretend operations, but it does it kind of in the format of coding, especially some of the more popular coding. I am, of course, not as familiar with it, and that's okay. But we will be using pseudocode as we go to kind of build our examples in a way that makes a direct connection to computer science. Okay. So properties of algorithms. So coming back down to algorithms, so let's give some names and properties that are important. So input, when we're working with an algorithm, and you can kind of course, relate this to computer science, we'll have this input value. So an algorithm has input values from a specified set. Then we do have output values. From the input values, the algorithm produces the output from a specified set. The output values are considered the solution, okay? Then we have what we call the correctness of an algorithm. That's important. An algorithm should produce the correct output values for each set of input values. And then we have finiteness. Wow, that is not how you spell finite. Finiteness. An algorithm should produce an output after a finite number of steps for any input. So doesn't go on forever. Then we have effectiveness. It's possible to perform each step of the algorithm correctly and in a finite amount of time. And then last, we want to have a generality in our algorithms. Sorry, that's like badly spelled, sorry. looks a little messy. There we go. Generality. The algorithm should work for all possible problems for this desired form. Okay, so we're gonna look at the pseudocode for the last example, okay? And we're gonna use the pseudocode to actually put this set of numbers. We're gonna put this set of numbers, we're gonna find the maximum. Okay, so the pseudocode that we talked about was here, and by the way, it's referring to the last example, but I did show you the pseudocode written out in format, and I'll show you that in just a second. Set a temporary maximum to be equal to the first integer of the sequence, and then you start comparing it. Okay, so temporarily, I am going to create the first, oops, too far. First sequence is going to be, sorry, my first max, oops. Oh, I'm sorry. It like got mad at me. There we go. Okay, the first max is going to be the very first term in the sequence. Okay, by the way, here, let me just label this so that we are comfortable in here. I'm going to zoom a smidge. This is our first term in the sequence called A1. This is A2, A3, A4, and then this one would be A5. Here, I'll put it below. So there's 5 terms in this sequence. And just so we're clear on some terminology, because we're going to see that here in just a second. A1 is 8, A2 is 4, A3 is 11, A4 is 3, and A5 is 10. So it's a general way of saying that the 5th term of this sequence, that would be A sub 5, and that would be the number 10. Okay, sorry, now back to our labeling. So labeling max right now is going to be the first term of the sequence automatically. And then we're going to compare this term to the next term of the sequence. So comparing 8 and 4, I see that 8 is bigger, so the max stays 8. All right, then I'm going to compare the max with the next term in the sequence. So I'm going to compare 8 with 11, and this time 11's bigger, so the max now becomes 11. Okay, so now I'm going to compare 11 to the next term in the sequence, which is 3. 11's bigger, so the max stays 11. They're calling this, by the way, the temporary max. Okay, then I'm going to compare the temporary max to the next term, which is 10. Oops, sorry. And 10 is smaller, so we're done. We've reached the end. Therefore, the temporary max becomes the actual max, and we have completed the pseudocode steps. This is the pseudocode written in coding format. So they gave a list of the procedure, and they tell us our inputs are a sub 1, 2, 3, and 3, all the way down to a sub n, and they are all integers. Then they assign the max to be a sub 1, and then they say that they're creating a variable I. I is going to go from the numbers 2 to n. So often we use a sub I to refer to the ith term in a sequence. That's a common mathematical notation. So I or j, those get used a lot. So when they say I goes from 2 to n, they're referring to a sub 2, a sub 3, a sub 4, a sub 5, all the rest of the terms in the sequence besides a sub 1, because a sub 1 has been assigned to be our temporary max. If our temporary max happens to be smaller than whatever I term we're looking at, the second, third, fourth, fifth, or sixth, then we reassign the temporary max. And by the time we're done, we go through all of the terms. It'll give us the largest term at the end. Okay, so let's, we're going to kind of work with this code and how we can write a little bit with it in terms of how we write our answers. But we're not always going to use that code to solidly write our answers. Let's move into searching problems. So a searching problem is to locate an element X in a distinct list of elements or determine if it's not even in the list. So a searching problem is useful for when you want to look, like maybe, for example, they say a library might want to check to see if a patron is on a list of those with overdue books. So the computer needs to search through a list of people who have overdue books and see if that person happens to be on the list. So there you go, search feature. Okay, so there's 2 types that we're going to look at: linear search. And a linear search locates an item on the list by examining elements in the sequence one at a time, starting at the beginning. So they just go one by one by one. So first they compare X with A1. So our name that we're interested in, is it the first name on the list? No. Okay. So then I'm going to go to the next name on the list. And then if it's not the next name on the list, okay, I go to the next name. And notice how they're sequencing through. So every time they compare, they're returning the position that they're on. So they're marking each position. And when they finally reach the value, if it happens to be the fourth name on the list, they'll return position 4. So position 4 is going to be the return for the answer once it's done going through its process. Keep going. If no match is found, we return 0. So we have to give something back. Okay, here is the algorithm written out. We are working with X being an integer. We're working with a sequence of numbers, a sub 1 through a sub n, and they are distinct integers. And then we have defined I to start with 1. Okay, now, now while I is less than or equal to n, and X is not a sub I, we return the next number in the sequence. So this is starting with the first term. And then if we do our comparison and it's not the one we're after, it pops us to the second term, and then the third term, and then the fourth term until we hit the magic number. That's what this says. If we hit that magic number, then we're like, cool, it's the third term. So the third one on the list is the match, and we return the location. Otherwise, we return 0, saying that it was not found on the list. Okay, so let's look at an example. List the steps to finding 9 in the sequence. Okay, so let's go ahead and go through this. So we're going to do a linear search. So we start with the first term. Now, when we go through these steps, we're going to kind of just check each one, and computer wise, we're going through location after location after location. So first place we start, we always start with the first one. So looking at the first term, we're trying to find 9, finding 9 in the sequence. All right. So I return the first location. No, there's nothing there. So as a computer, I'm moving on and I'm looking at the second location. So it's not that one. Second one. Nope, not that one. Okay. Third one. Nope, not that one. In fact, I'm going to keep going until I get here. So it's not third. Oops, sorry, I was a little off center there. So I can third, fourth, fifth, sixth. Okay, so fourth, fifth, sixth, but oops, sorry. But once I hit the 7th term, now I'm there. I go, oh, yes, as a computer, I see they match. Therefore, the location is 7. So I'm sending back the location of which number it is on the list, which place in the sequence of numbers it is. So it's the 7th place. All right, binary search, sorry. So to search for using a binary search. So now we're looking at kind of larger lists of numbers, and it might make sense to just kind of break up the list that we are looking at. All right. So the way they do that is I'm going to kind of tell you the steps, and then the steps will be written out in just a second right below. Actually, you should have it probably in front of you. I'm going to start by breaking this up into exactly half. There happens to be 16 numbers here. So I'm going to split it up into 1, 2, 3, 5, 6, 7, 8, 10. That's the first part of the list. And the second is 12, 13, 15, 16, 18, 19, 20, and 22. Okay, so it's between 10 and 12. Boom. So you split the list up. Okay, now here's what you do. So you compare the largest term on the first list. And then I noticed that in the first list, the largest term happens to be 10. So I'm looking at 10 and I'm like, okay, so since 10 happens to be smaller than 19, I just realized that's like really wonky. It's kind of, there we go. 10 happens to be smaller than 19. I'm going to no longer look at the first list. I'm going to restrict myself to just looking at the second list. So now I'm going to focus in on the second list, and I'm going to repeat the process again. So with the second list, I'm going to split it up. So I'm going to split it up as 12, 13, 15, 16. So I'm going right in half. And then 18, 19, 20, 22. And I compare again. I'm like, okay, so biggest number, they start with the biggest number on the second list. And they're like, okay, looking at this, it still happens to not be 19. So I'm going to again disregard the first half. Oops. There we go. Undo. I'm going to disregard the first half of the list. And I'm going to go ahead and just split up what's left here. So 18, 19, 20, and 22. And now I'm like looking at the first number on the list and I see that they work. So 19 does equal 19. And so I'm going to return that number as the location. Now that number happens to be the 14th term on the list. So they will return back the 14th term. So here, we're going to have to talk about how they kept track of placement. Let's go ahead and look at the list of the way they did the algorithm. So if the middle element is lower, so they split the list in two. If the middle element is lower, and they're referring to the middle on the first list. If that's lower, proceed to the upper half of the list. If it's not lower, then work with the lower half, split it in half and keep going, okay? Repeat this process until we have a list of size 1. If the element we're looking for is equal to the element in the list, the position is returned. Otherwise, it's 0. Okay, so here is the binary procedure written out. What I want to focus in on is the idea of I and J. I is the left endpoint of the, sorry, wow, my brain shut off there. The left endpoint of the interval, meaning it's referring to the term on the left of the interval. And then J is referring to the term on the right, the highest point for the right endpoint. Okay, so M is going to end up equaling I plus J divided by 2. That's the splitting of the list, okay? So I is going to be, if X is bigger than A plus M, so we're looking at this M term, this is the splitting of the list. We're looking at the right term of the first list. If that happens to be smaller than the value we're searching for, X, then we move into the next list and focus on the next list. And then the next list starts with M plus 1, the next term. So let me just kind of come back up here and label these just so we're clear. So in this list, I equals 1 and J equals 16. M is going to equal 16 plus 1 divided by 2, which is 17 divided by 2, which is 8.5. 2, 3, 4, 5, 6, 7, 8. So they're just going to return 8. So M equals 8. And they look at M equals 8. That's this term. This is the A sub 8th term. And they're comparing the A sub 8th term here with the number we're interested in. And they notice that it happens to be smaller. So they jump into this list. And the new list now starts with M plus 1. Which kind of rechanges our starting point to be I is kind of starting now at the 9th term, and then J is still at the 16th term. Then here, I is going to jump to the next term, and then J is still at 16. So the idea is that we keep changing the I value because it's going to change where we're at, which list we're looking at. So the I and J are indicating whether we're looking at a first half or second half list. It's going to kind of tell us where we're at in the sequence. It might make more sense when I get to step through it from the beginning, which I believe I gave an example here. Yay, I did. Okay, so we're going to step through this trying to locate 9. All right, so how many terms do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 terms. Okay, so first thing we're going to do, we're going to split it in half, right? All right, so I, to begin with, is 1, and J is 8. Okay, so first term, 8th term. Now, M, I'm going to go ahead and tell them what M is going to be. So when I add those two together and divide by 2, so 1 plus 8 divided by 2 is 9, divided by 2 is 4.5, but I'm gonna round that to 4, so M is 4. All right, so now I'm looking at the fourth term, okay? And it happens to be the fourth term does not return me the term I'm interested in. It happens to be smaller than the term I'm interested in. So I'm going to ignore the first group and now focus on the second group. Okay, so I'm changing my starting point. I is now going to start at 5. J is still going to be 8. Okay. And I could list J again if I wanted to, but because J is not changing, I'm going to go ahead and just leave it alone. Yeah, you know what? I could probably list it again. I could just start it down here. I equals 5, J equals 8. Now M, so I'm splitting again, splitting it up right here this time. Okay, so this is 8, 7, 6, 5. Okay, so 5th, 6th. So we're going to be, M is now going to be the 6th term. Looking at the 6th term, that's this term right here. And I'm comparing it to the sequence, the number I'm interested in, which is 9. Let me highlight it. And it's smaller than 9. So again, I'm going to discard this part of the sequence. And I'm going to start at I equals 7. So one more than this one. I'm looking at that to give me, so right, see that? I happen to be the next one up. I is now the next one up. So there's a direct connection between those. All right. J is still going to be 8. All right. And then M is now, we're splitting these two terms in half. So M is now 7. So I'm looking at that term and I see finally, yay, we did it. There it is. There's my magic X. So I'm going to return that location. So the location, oops, is 7th. Which was the last value for M. So that's how we could kind of list it out using the pseudocode. All right, the program written in the pseudocode. Okay, let's look at sorting. So it's important to sort elements and put them in increasing order. Even in fact, what we just looked at right there assumed we were in an increasing order situation. So it can be very important that we sort elements first, whether that be numerically or alphabetically. So I'm not going to read why it's important. I hope you're aware of why it's important. Let's look at some ones that we're more interested in looking at. The first type of sorting we're going to look at is called bubble sorting. Bubble sorting makes multiple passes through a list. Every adjacent pair of elements that are found to be out of order are interchanged. Okay, so we basically just slowly put it in order, one step at a time. It's a pretty slow process. This is the listing of the code. I'm not going to go through that. I'm going to go through the process instead. I'm going to bubble sort this. So here's what we're going to do. I'm going to start with, so this is going to be what's called my first pass. So I'm going to start with 3, 2, 4, 1, 5. And the first thing I'm going to do is I see that the first two are out of order. So I'm going to interchange them. So now I am at 2, 3, 4, 1, 5. And I'm like, okay, so I don't need to interchange the next two. We're good. So I'm going to interchange the next two though. These two are out of order. So I need to fix that. So that's going to be 2, 3, 1, 4, 5. And then the last two are good. I don't need to interchange those. So I'm just pairing them up. And so I'm not done though, because this isn't still in order. I have to do another pass. So at the end of the first pass, this is what I'm returning. So going step by step, comparing each term to the next one in the sequence. That's how we would return it after the first pass. Okay, now second pass. So starting with 2, 3, 1, 4, 5. Oh, okay. First two are good to go. Those don't have a problem at all. Second two, nope, that's a problem. So we're going to switch those. So 2, 1, 3, 4, 5. And Actually, there's nothing else. Nothing else is going to switch because 3 compared to 4 is good. 4 compared to 5 is good. So that's done. Second pass is done. Here's what I'm going to send back as a code. And I'm going to try it again. Third pass. Okay. 2, 1, 3, 4, 5. Okay. Looking at the first two. And those two need to be exchanged. So then I have 1, 2, 3, 4, 5. And I know that's done. This is in the right order. So okay. But we're not done as a computer. I'm just saying, okay, there's nothing more being interchanged. So after my third pass, I still have one more pass to do because I'm a computer and I don't know better. I'm going to make sure that the last pass is the pass where I don't actually interchange anything. And when I get to the point where I'm not interchanging anything, then I know that I've done it right. So I start with my list and I'm checking to see if I need to interchange anything. I do not. Therefore, I know I'm done. So it takes 4 passes for it to get it right, but it finally put the numbers in order. So these are the values you'd be giving as the answer for each pass. What would be the result? Okay, insertion sort begins with the second element. It compares the second element with the first, puts it before the first if it is not larger. Next, the third element is put into the correct element among the first 3. So each pass, we're comparing the next element to the previous ones and putting it in order. So when we're done, we're actually finished. We won't have to kind of be stupid like a computer. We're going to be able to be like, oh, okay, I get it. I reached the end because I was able to put them in order a little bit by little bit. Okay. Let's see. This is the code. It's starting to get a little bit more complicated. I think you can kind of see that. But let me show you the steps for how the insertion sort works. So same group of numbers. This time I'm going to, okay, so I start with my numbers here, 3, 2, 4, 1, 5. Okay, so first thing I'm going to do, I'm going to start with the second number and I'm going to compare it to the first number. And I'm like, oops, they need to be swapped. So I'm going to switch them here. The rest are going to stay the same. Make it look like a number 1. There we go. Okay, now I'm looking at this number here and I'm looking to see if I need to switch them. I don't. It's good to go. So the order is going to stay the same, but I'm going to go ahead. Oops, sorry. And in green, I'm going to show what is already good to go. What's been sorted. Okay, now I'm going to look at the 1 and I'm going to compare it to the rest. And I'm like, oh, nope, 1's definitely out of order. I need to put it in order here. Here, let me do it like that. Third step now. Okay, so 1 needs to go all the way to the front. 1, 2, 3, 4. Okay, and now I've got this term. And now I'm looking at the last term here. And I'm like, oh, I don't need to do anything. So my last step then is to write them in the correct order. And there we go. That's how we do an insertion sort. So it kind of makes it a little bit less cumbersome than the bubble sort, I think. Okay, string matching. So this is where we're looking for a pattern inserted among a string of numbers. Okay, so we call the pattern P if it occurs within a string T, which we're calling the text. Okay, so for instance, does the pattern 101 exist within this text? Can I locate it? And the answer is yes. Look, it's right here. So 101 is right there. It exists. And that happens to start on the 5th term. Okay, that means the way I say in string matching phrase is I say that this needs a shift of 4, meaning the first 4 terms of the text are not what I'm interested in. And then I have to shift over 4 terms of text, and then I'm able to start the pattern I'm interested in. Okay, so this example, they talk about DNA molecules, and they have these labels, TACG, blah, 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 blah. does CAG occur in this pattern? So I'm looking to see if CAG occurs. Oh, yep, it does. Right here, CAG. Okay, so how many terms is that? So it's the 6, so 5 terms over, so it needs a shift of 5. So I hope you see I'm just counting 1, 2, 3, 4, 5. That's where the shift of 5 is. 1, 2, 3, 4. That's where the shift of 4 is. All right. And then they do have the name for this. They call this the naive string matcher, and they have labels for everything. They call things T1 for the text, T1, T2, Tn, and then P1 through PM. Notice they have different end points because the pattern is supposed to be smaller than this. So they create that kind of labeling, and then they talk about how you use S to notate the way the shifting works. And they'll return the shift when we're done. All right, we'll talk about greedy algorithms in the next video.